share with you a really cool theorem called the angle bisector theorem, and its counterpart, the converse to the angle bisector theorem, which is also a theorem. Now always remember that the converse of a theorem might not actually be a theorem, but in some cases they are. And this is one of those cases. So I want us to celebrate the angle bisector theorem and its converse right now. Okay, first of all, let's see what the angle bisector theorem says. So it says, if a point is on the bisector of an angle, then it is equidistant from the sides. So if you have here a point C that's on the angle bisector, then what we know is if you measure the distance from that point C to this side and that point C to this side, they will actually have the same length. Those two line segments will be congruent. Now, what does it mean to measure the distance, the length away? Well, you take a point, and if you're looking at a line, you have to find the perpendicular line that actually is perpendicular to this side and passes through that point. And then the length of that line segment, that perpendicular, gives you the distance away that point is from this line. Similarly here, here's a line, here's a point. To find the distance from that point to this line, you drop a perpendicular and look for the length of that line segment. So what this says is, if you have a point C that's on the bisector, then this length and that length will in fact always be equal. So in this figure here, the challenge is for us to find
quite a huge tie.
CD, which is the length from C to D. Well, look at the picture and look at all the things that we're given. Notice that here we're given a little teeny mark here and a little teeny mark here. They're the same mark, which means that in fact the measure of this angle is equal to the measure of this angle. These two angles are congruent, and so that means that this BD is in fact an angle bisector for the angle ABC. Well, great. So since I know that, in fact, this is the angle bisector, and I see this point D is a point that's on that angle bisector, and notice that I see that this is a right angle made with this side, and this length is given to be at 13.6, and this here, this line segment is perpendicular to this line segment, then I know that this length represents the distance that this point is from this line. We know the distance from this point to this line is going to be the same as the distance from this point to this line, so this must be 13.6, so the answer is 13.6. And that's that. Isn't that easy? Let's try another one together and see how we can, in fact, find the measure we're looking for. In this case, I want us to now use the converse of the angle bisector theorem, which again, I'm reminding you, is true in this case, but converses aren't always true. And it says, if a point in the interior of an angle is equidistant from the sides of the angle, then it is on the bisector. So in this case, if you have a point C and the distance from C to this line is equal to the distance from C to this line, so namely these perpendiculars, these perpendicular line segments actually have the same length, then if that's the case, then C must be on the bisector of this angle. So this is the angle bisector of this. In this question, I want us to find the measure of angle RQS. So where is RQS? Well, RQS is right here. So I'm supposed to find this measure right here.
It's really far, yeah. I saved it for you to play it for you.
And all I'm given is the picture, but I am told the measure of angle PQR, the whole thing has measure 134. So that means that the whole thing, I'm told that this whole thing right here, that whole thing is 134 degrees. The whole thing. I want to find this little piece of it. Well, let's see if we can figure out what that piece, how that piece relates to the whole. Well, let's take a look at the image. I'm given that this line is perpendicular to this line, and I'm given this line is perpendicular to this line. So not only are they perpendicular, but I actually see that this point S, way up here, the distance from that point S to this line, since this is perpendicular, I can read it off of here, is 63. And the distance from S to this line is the perpendicular distance, but look, this is the perpendicular line, and it has distance 63. So, since these two lines have equal length, we can now apply the theorem. We see that, in fact, this must be on the angle bisector. Namely, this angle here must, in fact, be congruent to this angle here. This bisects this whole angle. And since this angle here is congruent to this angle here, and they make up this whole thing, they must have the same measure, which means that the measure that I'm looking for must be half of this. And so the measure that I'm looking for here must equal 1/2 of the measure of angle PQR, which will equal 1/2 of 134 degrees, which of course is 67 degrees. And so the measure that we were looking for in this example is 67 degrees, and we found that by applying the converse of the angle bisector theorem. The angle bisector theorem and its converse, which is also a theorem, turns out to be very, very handy when we have a point that's sitting inside somehow an angle, and we know something about that point's distance to the sides. If we know that those distances are equal, then we know that point is on the angle bisector. And conversely, which is the angle bisector theorem, if I bisect an angle, then in fact any point on that angle bisector will be equidistant, perpendicular distance to the sides will be the same on both sides. Have fun looking at different types of applications to the angle bisector theorem and, of course, its converse. Have fun thinking about math. I'll see you soon.
I love you.
You know, there's a really cool theorem called the in-center theorem, which basically says that if you take a look at the angle bisectors of each of the three angles of a triangle, those three lines actually meet up and meet at a single point, and in fact, that point is equidistant to the sides of the triangle. Really cool and not at all obvious, but in fact, true nonetheless. I want us to take a look at that fact and apply it to find a bunch of measures. Let's check it out. So, given this picture right here, we're told that segment FQ and line segment HQ are angle bisectors of triangle GFH. Our challenge is to find each of the measures. And the first measure I want us to take a look at, and I'll write it right here so we can enjoy it together, is the distance from the point Q to the line segment GH. So that's the first question I want us to pose. Now, what do we know? Well, we know that Q is on the angle bisector of this angle and of this angle. So what does that mean? What that means is that this angle is congruent to this angle, and this angle is congruent to this angle. And that's all we know. Now, I want to find the distance from Q to GH. Oh, that's this side right here. So what does that mean? That means that what I have to do is I have to take this point Q, and I've got to actually drop a perpendicular to it, which really kind of means rise up a perpendicular. Hard to do visually, but I'm going to try it right now live, best I can. It's not bad. If I do that, it makes it look that much better, right? Perfect. So that's how you find distance from a point to a line. You look at the line that's perpendicular to the given line and passing through the given point, and then that segment has a length. That length represents the distance. So I want to find that distance. That's the first question. So that's this question right here. Well, how could I find it? Well, I could use the in-center theorem, which says that since I have angle bisectors coming together and they're meeting at this point, so therefore that's the point where the angle bisectors meet, I know that point is equidistant from the sides of the triangle. And check it out. Here I see the distance from Q to this side. Since it's a perpendicular marking here, I know this is the perpendicular line, so this is the actual distance, and that distance we see is 5.9, which means this must also be 5.9. So without doing any more work, I see 5.9 for this distance, and that's what this equals. So this equals 5.9, and we're done by an application of the in-center theorem. Now, here's another question while we're here. Let me just pose question 2. So here's question 2. Let's find the measure of angle QHF. So let's see where QHF is. QHF. Okay, so we're looking for this measure right in here. You want to know what that is? Well, this seems a little tricky, right? Because I don't seem to have maybe enough information. But if we take our time with it, I think we'll see that we actually have lots of information. First of all, let's remember that this, in fact, is an angle bisector for this angle right here at F. And notice that we're told that this is 23 degrees, which means automatically this must be 23 degrees because it bisects the angle. So the measure of this side must be the measure of that side. And so this entire thing right in here must have a measure that's double this, which is 46 degrees. So that span right there has a measure of 46 degrees. Oh, and look, we know what the angle is on G. That's 100 degrees. We know the angle here at F is 46 degrees. Well, then we can find the measure of angle H, because, of course, we know that if you add up the sum of the angles of a triangle are always going to be 180. So, in fact, this angle right here, which we know is 46 degrees, plus this angle right here, which is 100 degrees, and if we add to it the measure of angle F, H, and G, that has to give me 180 degrees. So now I can find not what I want, but I can find the entire angle, which is overshooting a bit. But remember, Q bisects this angle H, and so therefore all I have to do is then take half of my answer, and I get what I want. So what happens here? Well, here I see 146 degrees plus the measure of angle FHG equals 180 degrees. And so if I subtract 146 degrees from both sides, I see that the measure of angle FHG is equal to 34 degrees. So that's the whole angle. I only want half of it. You see how this plus this equals the whole? And so therefore this is going to equal 1/2 of 34 degrees, which is 17 degrees. And so the answer to this question is 17 degrees. And we've answered the questions. So look how the geometry is rich when we're thinking about a triangle. Really interesting to see all the possibilities. And if you're looking at a couple of angle bisectors, they not only meet at the same point, all three of them in fact, but if you look at the distance from that point of intersection out to the sides, the three sides of the triangle, that distance in each case will be the same. Well, the triangle holds a lot of structure, and as we're seeing these different components to triangles, we're seeing more and more, deeper and deeper into the world and notion of triangle. Have fun making discoveries about triangles on your own, and I'll see you soon.